So let's see how these are going for you. First one here, we need to find this angle here. We're not given it like we sometimes are. So to do that, we're going to look at this. Of course, the height of this triangle is the difference, the 0.750 minus the 0.200. So this is 0.550 here. And this side is half of the difference between the 0.90 and the 0.20 and the other 0.20. So the whole way across from here to here is 0.5000. That's the 9 minus the 0.9 minus the 0.2 and the 0.2. Half of that is 0.250. So I'm going to pause. Any questions on where those measurements came from? Which one? The bottom one here? Okay. This one or this one? Okay, because you have 0.2 here. That's 0.500. So now that we have those, I'm going to find this angle here. That angle, if I take a line from the center of the circle down to that intersection of the tangents there, the point of the V, those two lines would be parallel. So this angle and this angle will be the same. And this is actually the angle I want. I really don't need the whole angle of the V. So to get this angle, I'm looking at, I'll call that theta for now. I'm looking at this would be the opposite side, and this would be the adjacent side. So I'm dealing with a tangent at the moment. So tangent of an angle is opposite over adjacent. We are looking for the angle. We don't know the angle. We do know the opposite side is 0.250, and the adjacent side is 0.550. When we are looking for an angle, what do? The inverse of whatever trig function we're doing. It's the tangent of that angle that we have. So to find the angle, we do the inverse tangent. Inverse tangent and tangent will cancel out. So there's this tangent here. On the other side, we have the inverse tangent of the 0.250 divided by 0.550. Which is 24.44 degrees. So back up to the problem, that 24.44 is this angle here. So the heart of this problem is this triangle here in brown. So I'm going to redraw that triangle. That's a right angle there, because it's the radius of a circle going to a tangent. So that's a right angle. We know that the radius of this is going to be half the diameter. Diameter is 450, so the radius here is going to be 0.225. And we know that angle of 24.44 degrees. So what we need to find is this side here, which is the hypotenuse of that triangle. According to this angle, the 225 thousandths is which side of that? Which leg? Opposite or adjacent? That is the opposite. So we have opposite and hypotenuse, which tells us we are going to deal with the sine. This angle here is the one we found up here. From the triangle? That's this one here in brown.
And you can find the hypotenuse for the adjacent from
You could find the, yeah, you could find the adjacent, but you don't need it for this problem. Because what we're looking for is this distance that this is above. So we have to have this distance, which we're given. We're finding this distance, and then this is just a radius. So now, sine of an angle is opposite over hypotenuse. We have the 24.44 degrees. The opposite side is 0.225. The hypotenuse is what we're looking for. So now in this case, we're looking for a missing side. In this last problem we did up, the last portion we did up here, we were looking for a missing angle. When we were doing the missing angle, we did the inverse trig function. When it's a missing side like this, we make it a proportion. And to do that, we put our trig function over 1. And then we cross, multiply, and divide. So it's 1 times the 0.225 divided by the sine of 24.44. Which is going to give me 0.5437. So this is 0.5437 inches. So now you get the total height to the top of that ball. We've got the 0.200 here. We've got this here, which is what we just found, the 0.5437. And we've got from here to here, we've got the radius of 0.225. So that total height, we have to add them up down here. 0.200, 0.5437, 0.225. Bless you. It's 0.9678. So that 0.9678 inches we just found goes from the bottom all the way to the top, up to here. So to find x, we just need to subtract off this 0.750. So we will subtract 0.750 inches. So 0.2187 inches is how far that ball is sticking up out of that V block. Any questions? Yeah.
I don't see how you, well, explain how you got 24.44 for the angle for the little triangle.
Okay.
On the inside there. If you found that for the other one, how did that?
Because this line here is a vertical line, right? From the center of the circle to the intersection of those tangent lines, the point of the V, that would also have to be vertical. Because if that's a symmetrical V, the center of that circle is set directly above the point of the V. So those are both vertical, which means those lines are parallel. So what this angle is has to be the same as this angle. Does that make sense? Basically, is if you have parallel lines, cut by a transversal, this angle and this angle will be the same. That's basically what it is we found this triangle here, and we're using it. Once we found that angle, this angle's got to be the same. Now, it's actually a very common, there's a couple of common themes here that were in this problem. The first one is vertical and horizontal. In these problems, we must create right triangles. And one theme when you're creating right triangles is if you can find a vertical dimension and a horizontal dimension that intersect, they have to intersect at a right angle. So there's one of your right angles. So that's one way of constructing right triangles, is to look at vertical and horizontal dimensions that come together. The second, excuse me, is tangents to a circle, we know that a tangent to a circle is going to form a right angle with the radius of that circle. So if you have a line that's tangent to a circle, which was, that V block on the edges of that circular stock, you know there's going to be a right angle there where that radius hits that tangent. So there's another place you can find a right angle to construct your right triangles. The third theme that we saw in this problem, it's not about right angles, but it's about finding angles. If you have a surface, let's draw it like this. Let's say we have a surface that forms a certain angle to the horizontal. It'll form that exact same angle to any horizontal. So if I have another horizontal up here, it's going to form that same angle there and there. So if you know the angle of a surface to a horizontal line, it'll have that same angle to any horizontal line. And likewise, you have a vertical surface, and you have a feature that has an angle to that surface. It'll have that same angle to any other vertical surface. Those angles will be the same. So that's how we were able to carry that one angle through from that triangle into the V. Those are pretty simple concepts, but sometimes they're really hard to see within a picture. So coming back up to this picture here, we need to find the right triangle. This one isn't quite so bad to find. What line do I have to draw in to complete the right triangle here? Yeah, from here over, right? That's the only angle I'm given at 38 degrees 40 minutes, so I know that has to be one of the angles of the right triangle. The only way I can create a right triangle from that is to go off the vertical here, so I have to create a horizontal. Again, you know that a horizontal will always be perpendicular or form a right angle with a vertical. So in that triangle, we know that this side is 0.850 inches, because it has to be the same as this dimension here. So 38 degrees, 40 minutes, 0.850 inches. What we were looking for there was that dimension x that was over here. To find it, we would need to know how much to subtract off for this. So that is this side right here. So according to the angle we have, the 3840, I don't know why I put a degree symbol there. Up a bit. And as you can see from here, well, he's getting that written down. This dimension is the same as this dimension of the triangle. And we have to have that dimension so we can subtract it twice from the 2.5 to get our missing dimension x. So, excuse me, according to our 3840, the 850 thousandths is which side of the triangle? It is the opposite side. And this would be the adjacent side. So we have the opposite and we are looking for the adjacent. That is a tangent. So write down, I always write down the definition. Definition of tangent. Tangent of theta equals opposite over adjacent. And then I put in my numbers. Tangent of 38 degrees 40 minutes equals 0.850 over the adjacent side is what I'm looking for here. Put this over 1. Since I'm looking for a missing side, I make it into a proportion so I can cross, multiply, and divide. 1 times 0.850 divided by the tangent of 3840. Gives me 1.062. So this is 1.062 inches. So back up to my original picture. This is 1.062 inches here. This is also 1.062 inches. Good point. We had to assume this was symmetrical. Otherwise, there's no way we could do it. So we combine those. That's 2.124 subtracted from the 2.5, which is 0.376 inches. So X is 0.376. What do you think on these? I mean, the tough part really is finding those right triangles and picking them out. Usually it's this time and this point in the course where I slow things down a bit for you. And that's what we're going to do today. Is I'm going to do a couple of examples out of the homework, and we're going to keep the same homework assignment. And is there anybody that actually did get all of the problems done? Okay. I'm going to do one of the even problems. So this one's in the packet on page 360. This is problem number 18. Let's see if I can draw it. Number 18. I butchered the drawing a little bit there, but that's okay. So what we have is the diameter of each ball is 50 millimeters. We're given the space between the balls here of 40 millimeters. We're given from here to here of 207.30 millimeters. And we're asked to find this angle here, X. You'll see that when they drew this, they actually drew it kind of circled there instead of coming to a point. Do you know why they do that? Well, there's a radius on the tool, yes. Also, it's a stress relief. You can get a tool that'll make a perfect sharp corner down in there, but you don't want to do it because whenever you have sharp corners like that, it's called stress risers. The amount of stress that's in that object when force is put on it, of course, is inversely proportional to the width of it. So the thinner it gets, which of course here is its thinnest spot across there, the higher the stress is. And if you come to a sharp point in the surface of it, there's a stress riser, which means that sharp point is it's a weak spot where it's more likely to break. And so by rounding it slightly, you avoid those stress risers.
I will say we use two pins like that in a dovetail every day I learn on every single rifle barrel and check it.
Okay.
Gauge block.
Okay.
It actually keeps-
Oh, sure. So, looking center to center here, I'm going to find that center to center distance, which isn't that hard to find, because I know the diameter is 50 here. So from here to here is just one radius of 25. And here to here is a radius of 25. So center to center, from here to here, is 40 plus 25 plus 25, which is just 90 millimeters. So with that, I'm now able to construct this triangle. Remember, that was one of the things I told you to watch for, is a tangent to the surface of a circle. They'll always form a right triangle or a right angle with the radius. And so this is it. The bottom surface is tangent because the circle is setting on it. And that's the radius. So we know that radius is 25 millimeters. And we can find this distance. We've got the 207.30. If we subtract the 90, we get 117.30. Now that is split evenly between each side. Again, we have to assume this thing's symmetrical. So we're going to have to divide that by 2. So that's 58.65 millimeters. So this is 58.65 millimeters. Do you see where I got those dimensions? I took this, I subtracted that. The 207 was given. Subtracted that, then I had to divide it by 2 to split it up. So now what I have, that red triangle there, I have 58.65, and I have 25. And I'm looking for this angle. That's not angle X at this point. X is going to be double that. So I'm going to call that, we'll just call it theta for now. According to theta, this is the opposite side and this is the adjacent side. So that's going to be a tangent. Tangent of an angle is equal to the opposite over the adjacent. I don't know the angle. That's what I'm looking for. The opposite side is 25 millimeters. The adjacent side is 58.65 millimeters. So now I'm looking for an angle. What do I do to find the angle? Inverse. It is tangent, so yes, we do the inverse tangent. So our angle, theta, is the inverse tangent of 25 over 58.65. Now, those of you with fraction calculators, if you're trying to enter that in the calculator, you cannot use the fraction key. Because once you hit the fraction key, most of your calculators will not allow you to put a decimal in the denominator. So you have to do a second tangent or a shift tangent, depending on your calculator. Then just in the parentheses, just put in 25 divided by 58.65. Close your parentheses. I said there are some calculators that will allow you to put a decimal in the denominator, but most of them will not. So we get 23.086 degrees is theta. Yeah, it doesn't work if you use the decimal in the fraction. It divides it up. So that 23.086 degrees is this angle here. That's half of x. So if we just multiply by 2, we get x is 46.17 degrees. What do you think? want to take a peek at a problem like number 20. Most of the problems we've done so far, you've had to divide stuff up within the part. Number 20 is one where we're going to have to add pieces on outside of the part. So for number 20, so we've got it is saying that all radii are 0.500. It says 0.500 are 3 places. So that's, since there's only 3 centers marked here, that's assuming all 3 circles are 0.5 or half an inch radius. From here down is giving us 3.31. And across here is giving us 6.080. They want to find this angle here. Why? To find that angle, I would look at this as being a big right triangle. That's a right angle there. Now again, it's not shown, but we're assuming by the drawing that this is a vertical dimension and this is a horizontal dimension. So if we extend them till they intersect, it should form a right angle, or has to form a right angle. I'm going to extend that point out there, and then this point out here. This corner here that I added does not affect either of those dimensions. This point is going to affect this bottom dimension here. I've got to figure out how far that sticks out. So what I'm going to do is down here, I'm going to form this triangle. This here is a radius of the circle, 0.250. From there, what do you think we should do? Oh, you're right. I shouldn't have divided that in half. I was reading that 50 is diameter, but you're right. That is a 0.50. Thank you. Actually, looking at this, my strategy is not going to work. Adding onto the outside isn't going to do this one. Because looking at this, I don't know any of these angles. I would have to have one of the angles in order to find how far this stuck out here. So that strategy is not going to work. So a different approach. One approach you can use when you have circular corners like this, if all of the radii are the same for all 3 circles, you connect the centers of the circle. So the question is this side here parallel to this side? Yeah, they are, because this is 0.5 and this is 0.5. Yes, this triangle, the red triangle I just drew in, would be similar to the one that I just erased, where I expanded it out. In this red triangle, what do we know? Well, we know that this is 0.5, right? And that's 0.5. So we can subtract 1 from the 3.310. Yep, we'll do the same the other way. So this is 0.210. And the same thing, this is 0.5 here and 0.5 there. So we subtract 1 from the 6 to make it 5.080. So we have those two dimensions, and y should be the same as this angle here. So we have opposite and adjacent. So tangent of an angle is equal to opposite over adjacent. The angle is angle y. Opposite is 5.080. Adjacent is 0.210. And we're looking for the angle, so we're going to do an inverse. The function is tangent, so it's an inverse tangent. So inverse and tangent cancel out. Y equals the inverse tangent, so second or shift tangent, 5.08 divided by 0.21. 87.63 degrees. So that's why. Something didn't work out right there. You're right, 2.31. Thank you. 2.31 down there makes a big difference. So 5.08 divided by 2.31. 65.55. There you go.
That's not the same angle as that big angle.
This angle here will be the same as the angle up here, which is the same as this angle. You can look at it this way. If I extend this line out, since these two lines here are parallel, this angle and this angle are the same. And since these two lines are parallel, this angle and this angle are the same. Yeah. Yep. The intersection of the two tangents has to be supplementary to the central angle. All that. So once again, page 358 through 361. If you work on the odds, it's 1 through 23. So the hardest part is finding out where the right triangles are. You can see on this problem here, I tried one right triangle, it didn't work, so I had to go back and try a different one. The first thing you try isn't always going to be able to give you the answer, so be patient with them. Sometimes you just have to start drawing lines and find something you know is a right angle and draw a right triangle off of it and see if it works. If not, find a different right angle. What's that? Yeah, sometimes you can do that. Sometimes you draw on a right angle and you just can't get, it doesn't give you the information to get to where you need to go.